Okay, so our last speaker for this morning's session will be Stacey Jeffery from Amsterdam, and she will talk about how to test a quantum computer.
Thanks. So the problem that I'm going to talk about is going to be very relevant in the near future because we expect that in the next few years, some experimental group is going to develop a quantum computer, maybe not a universal one, but some kind of a quantum computer. And they will want some way of testing whether they have actually done this out of scientific curiosity, but also to prove to the rest of the research community that they're the first to achieve this task. And maybe even more practically, some of the people claiming to have built a quantum computer over the next few decades will be companies that want to sell the quantum computer to you. And there's actually already a company in Canada that will sell you a quantum computer for $15 million. And there's been a lot of debate over whether the device that they're selling is actually doing something quantum. And I don't know about you, but if I spent $15 million on a quantum computer, I would want to know for sure that it's more powerful than my laptop. Now, most of us won't be buying a quantum computer, but some of us will, in the next couple of decades, delegate a computation to a server that does have a quantum computer. So IBM has already announced that they will have a cloud quantum computing service. This is not necessarily depicting IBM. Perhaps it's one of their cheaper competitors. But if you're paying someone to do a quantum computation for you, you're sending them over some data and asking them to perform some computation, and they send you back the answer. Not only might you want to be sure that you're getting your money's worth, but you might also be making some important decisions depending on the output of the computation. So you really will want to verify that you're not just getting some kind of random number, that this is actually the result of whatever quantum computation you wanted to do. And so both of these fit into the scenario of testing a quantum computer. And you might think about something like benchmarking, but we're considering a more adversarial scenario. We don't want to assume that just because our computer passes a few tests, it's working as expected. And one motivation for that could be you might buy some quantum hardware, some quantum computing hardware that you're going to use for cryptographic purposes. And in that scenario, there really is the possibility that someone has tampered with the equipment in order to trick you into thinking that it's working correctly, but in fact, whenever you use it for, say, encryption, there will always be some kind of a backdoor so people can eavesdrop on your messages. So we're considering this kind of adversarial scenario where we think the quantum computer might really be trying to trick us, and we really want to verify that it's doing the right computation. So I will talk about the general problem of testing a quantum computer, which has already been discussed this week, for instance, in Masahito's talk. So I'll talk about the settings in which we can actually achieve this, and I'll also mention some recent results by myself and my co-authors, Alex Grillo, who's here in Paris, and Andrea Coladangelo and Tama Vidic from Caltech. But before we talk about the big problem of testing a quantum computer, we can first consider a still very difficult but more fundamental problem of experimentally verifying quantum mechanics. So suppose you have some system and you hypothesize that this system always outputs a state pointing in some certain direction. So it always has some particular internal state, and you want to test this hypothesis. So it could be that you're an experimentalist and you have some physical system and you think that it always creates certain quantum states and you want to test this. Or it could be that this is some quantum hardware that you bought. Maybe it's cryptographic hardware and you want to test that it's really working as advertised. So what would you do? Well, you would keep making this system produce states and perform some measurements and do state tomography to determine if your hypothesis is correct. But the problem is that this assumes that you have some trusted quantum measurement device. And this is a measurement device. At least it's what I found when I Googled measurement device. So, but there's many scenarios in which you maybe don't want to trust a measurement device. So for example, if you only have one quantum hardware store in your town and you bought this state preparation device and this measurement device from the same place, you certainly don't want to use their measurement device to test their state preparation device. I mean, it could be possible that this measurement device actually just ignores whatever particle comes into it and just produces the correct output statistics that you think you should get. Another possibility is if you're an experimentalist and you're trying to actually test quantum mechanics, you can't assume that your device, your measurement device, follows the laws of quantum mechanics in order to prove quantum mechanics. The point is that if you are, and we all are here, classical people, we need to interact classically with an experiment. So we should really be modeling any kind of experiment where we want to test a hypothesis as having a classical input and a classical output. So the input might be some setting on the measurement device. This could be a description of an observable that you want to measure, and you don't make any kind of assumption that that's actually the measurement that will take place, but you know you can set certain knobs on your device, and so you can give that some kind of a label that describes a measurement. So your input is going to be some description of a measurement setting, and your output will be some kind of classical measurement result. And this is how we should really be modeling any kind of quantum testing that we want to do. But the problem is that this is actually, in some sense, kind of hopeless, because you can never be sure that if you have this sort of classical black box, you can never be sure that there's not just a classical device inside of it simulating whatever output statistics you should get. Especially if we have a small system where it would even be efficient to simulate it, there's no way to guarantee that there's anything quantum mechanical going on in this box. But we do know of another scenario where we can actually test quantum mechanics, and that's when we have two boxes, and there we can do a Bell test. So if we have two separate quantum boxes, and we hypothesize that they share entanglement and can do quantum operations, but we don't allow them to communicate, then we have these ways of actually letting these boxes prove to us that they're quantum mechanical. So we've already seen, I think several times this week, this famous example of a Bell test, the CHSH game, where the players can win this game with higher probability if they share entanglement than without. And this gives some way for these, for us to actually prove or verify, using only classical inputs and classical outputs, that something is at least quantum mechanical in some sense. So there is hope. Let's get back to the problem of actually testing a full quantum computer. So in this scenario, we have an experimentalist who has her hands on something that she hypothesizes is a quantum computer. So she might have built it in her lab, or maybe someone gave it to her. And she can interact with it classically, so she can decide on any quantum computation that she wants to do, specified by a quantum circuit. So this Q could be a description of Shor's factoring algorithm, and also an input to that circuit. So X could be an integer. And the output will be, hopefully, the answer to her computation. That's the hypothesis anyway, and she wants to test that hypothesis. And so we want to come up with the following kind of verification protocol, which is some interaction between what we call a verifier, the person who's testing the hypothesis, and the prover. And the prover should have a quantum computer. So the verifier has an input, which is a description of a quantum computation, and an input to that computation. And the output will be either a bit indicating the answer to the computation, or a reject symbol. And we require two properties. So first, we require that if the prover follows the honest protocol, so if this prover is behaving correctly, at the end of the protocol, the verifier will learn the correct output to the computation. Meaning that if the prover is willing to actually honestly work with the verifier, she will learn the output to the computation. And of course, this means necessarily that the prover must have a quantum computer for this protocol to work. And the second property we want is soundness, meaning that even if the prover is cheating in any arbitrary way, the prover should not be able to trick the verifier into outputting the wrong answer. She can only still get the right answer somehow or reject. So if the prover is cheating and trying to make her get the wrong answer, she will detect this and output reject. And we don't require this to hold with perfect certainty. We just require that there's some constant C called the completeness, which if the prover is honest, she'll always get the right answer with probability C. And then some other parameter S, which is the soundness, meaning that no matter what the prover does, he can't convince her to output the wrong answer except with probability S, and there should be a gap between these called the soundness-completeness gap. Okay, so this is the problem that we're trying to solve. And the way I stated it, it's actually, we don't know if we can do this. And it really could be that this is impossible. So we have to, at least as far as we know, we have to relax something about the scenario. And so one thing that we can do is we can give the verifier some quantum power. If we give the verifier a full quantum computer, then the problem is obviously easy. The verifier will just do the computation herself. But if we give her some trusted quantum device that is even very simple, we can already do this. So this could be a simple single qubit measurement device. It's also possible if we give the ability to create a small set of single qubit quantum states. So this is one scenario. And the other scenario in which we can accomplish this is related to Bell tests. And it's when we have a classical verifier and two provers. So we have two provers who each have a quantum computer, and they share entanglement, but they're not allowed to communicate. And in that setting, also, the verifier can verifiably delegate a quantum computation. So let's compare these two scenarios. The first scenario, one really nice thing is that even giving a very, very small amount of quantum power to the verifier is already very powerful. And many of there's several protocols in this first regime, and many of them really just have the prover really just running the quantum circuit as normal with occasionally doing something extra. And so there's a very little overhead in some of these scenarios. And so we can get very efficient protocols in this scenario if we let the verifier have a little bit of quantum power. But of course, the downside is the verifier is not classical. And in some settings, that might be fine. But like I've already mentioned, some settings where you wouldn't want to have the verifier trust a measurement device. In particular, it would not be practical to require everyone who wants to use a cloud quantum computing service to have a quantum measurement device and know how to use it. And so the second scenario has the huge plus that the verifier is classical. And the first protocol to do this by Reichardt, Unger, and Vazirani was a huge breakthrough because before this, we did not know if it would be possible for a classical verifier to have this kind of control over quantum systems. So that this first paper that achieved this was called a classical leash for quantum systems because it really gives a way for a classical verifier to really kind of gain a handle on any quantum system. So this was a very big result. The downside with this result was the overhead. So we do require that the overhead be only polynomial. So if you want to delegate a quantum circuit of size g, the complexity should be some polynomial of g. But unfortunately, in this first protocol, it was a polynomial with quite a large degree, meaning that if you have a circuit with 2 or more gates, this is impossible. So this was, theoretically very, very interesting, but in practice, totally impossible. So, but luckily, there have been some improvements since then. So I mentioned we have these one-prover quantum verifier protocols, and I won't talk very much about them. There's several using different techniques. I'll talk a little bit about the one by Anne Broadbent, which is a building block in our protocols. And then we have, in the true prover setting, we have this first breakthrough result, and then we have a significant improvement to something that is still impossible, but like really, really much better. And I think I maybe am actually missing something here. So I sort of learned from Masahito's talk that maybe there's also his result up there might also have a two-prover protocol that has g to the 4 log g with only 2 provers. So here, then we also have more than 2 provers. And here we can also get as good as g to the 4 log g. So also, I guess in the 2 provers, there should also be a g to the 4 log g. And this is if we extend to a polynomial number of provers. And so g to the 4 now becomes like thoroughly possible, but also thoroughly impractical. And then there's one other way that we can kind of improve these things. There's a different sort of task called post hoc verification. And here we could get down to g to the 3. But this is kind of a different setting where the provers have to come together and create an entangled state that depends on the computation they're going to do before then separating and doing some kind of a protocol. So it's a different scenario. So our contribution is to, with only 2 provers, get down from, I guess, actually g to the 4 log g It's a lot less impressive, though. It's kind of sad. But to G log G. So this is the first efficient protocol for a classical verifier to delegate a quantum computation. And this is almost optimal because, of course, we couldn't run a G-gate circuit in less than linear in G. And so another nice thing about our protocol is our protocol works by starting with a protocol due to Broadbent in the first regime, where we have a quantum verifier. And it inherits some of the nice simplicity. So our protocol also, a lot of the prover's work looks like just running the computation normally. And then there's just a small amount of overhead. So that's where we get this efficiency. OK, so in the remainder of my talk, first I'm going to very briefly introduce this protocol of Broadbent on which our protocol is sort of based. And second, I'm going to talk about rigidity games, which are some kind of, well, the CHSH game is one example. And we develop a new kind of rigidity game, which we combine with and Broadbent's protocol to get our new protocols. OK, so first, I'll talk about Broadbent's protocol, where the verifier has some small quantum measurement device. And I'm not going to talk about the details of this protocol. I'm really just going to introduce what we need for our purposes. But in this protocol, well, Anne calls it the EPR protocol, and she actually used it as a proof technique to prove the security of possibly a more practical protocol. But this version of the protocol is very nice for us. So we have the verifier and the prover are sharing n plus t EPR pairs, where n is the number of qubits in the input and t is the number of non-Clifford gates in the circuit. And the verifier's quantum behavior is just that she is going to measure her EPR pairs in some observables. So for example, she might measure her first EPR pair half in the Z basis, so that's like a computational basis measurement, and then that would just project the other half onto some state. And she's going to do these measurements for two kind of distinct purposes. So one, the first n will be used to initialize some kind of input on the prover's side. So here you could see she's just sort of initialized a qubit to 0, but it's under a one-time pad. And then the other last t are going to be used to initialize certain states that are used to help perform t gates. But I won't say any more about that. So the point is that the verifier will choose in some way some observables to measure on her EPR pairs and get the outputs. And that's really all of the verifier's behavior. And these observables are going to be chosen from these two sets, depending on if it's the input qubits or the qubits that are used for helping perform t gates. And the important thing is that these sets of observables are Clifford observables. That will be important later. Okay, so the takeaway from this is just we have this protocol that allows a verifier with a measurement device to simply through doing some classical work and measuring certain observables interact with this prover and verifiably delegate a quantum computation. Okay, so now switching gears, I'll talk about rigidity games. And in particular, I will mention a game called the magic square game. So a magic square is a 3x3 binary matrix in which all of the rows sum to 1 and all of the columns sum to 0. And such a matrix is not possible because if it were, then you could add up all the entries by first adding up the columns and then adding up the column sums to get 0. And if you added up the entries in a different order, you would first sum the rows and then sum the row sums and you would get 1. And of course, since addition is commutative, there's no reason you should get different outcomes by adding things in different order. So a magic square cannot exist, but suppose a couple of your friends claim that they have found a magic square. And you're skeptical about their claim, but they don't want to show it to you because they actually want to patent it, obviously. And so you want a way of testing that they really have a magic square, but without them having to reveal the whole thing to you. And so what you can do is you can separate them and ask one of them to give you one of the rows. So you'll get 3 bits, which are claimed to be the row of a magic square, one of the rows chosen at random. And since this is apparently supposed to be the row of a magic square, it should sum to 1, so you'll check that. And the other prover, you're going to ask for a column of the magic square, and he's going to send you 3 bits, which he claims to be a column of a magic square. And so you will check that they sum to 0, because that's the condition on a column of a magic square. And so this is showing you that the first prover has a matrix where the rows all sum to 1, and the second prover has a matrix where the columns all sum to 0. And now you want to be sure that they're the same matrix. So this row and column overlap in one position, and so you're just going to check that, in fact, the bits they returned at that position are equal. And you'll check these conditions, and you'll say they win this game if they satisfy all of these conditions. Now, since a magic square cannot exist, this game cannot be won, at least not all of the time. So you're randomly making a choice of a row and a column, so it could be that they get lucky, but they can't have a winning strategy for every possible row and column that you ask them. And so they cannot win this game with probability 1 if they are classical players. The best they can possibly do is win with probability 8/9, and that's true even for randomized strategies. And the reason that we care about this game is that if they share entanglement, there's actually a strategy that allows them to win the game with probability 1. So they could, in some sense, fool you into thinking that they actually have a magic square. And in this strategy, we'll have them share 2 EPR pairs. And their quantum strategy will also be described by a 3x3 matrix, but now the matrix will have, the entries will be observables. And in a minute or so, I'll say a little bit more what it means to measure an observable, but first let me describe the strategy. So this matrix of observables has an important property, analogous to a magic square. All of the columns, if you take the product of observables in a column, you get the identity. And if you take the product of observables in a row, you get minus the identity. So these are analogous to the constraints of a magic square. And the strategy will work as follows. So the first prover will get an index of a row. So suppose it's 1. So he'll look at the first row of this matrix, and then he's going to measure all of these observables on his 2-qubit system. So he first measures the first observable and gets a bit, and that's going to be his first bit of output. And then he measures the second observable on the same 2-qubit system and gets out a bit, and that's the second bit of his output. And then finally he measures the third observable, again on the same 2-qubit system, and gets a bit, which is the third output. So these are the 3 bits that he returns for his output. And the second prover similarly will do the same thing, except he'll look at the corresponding column, the column that corresponds to his input. Okay, so what does it mean to measure an observable? So we're going to only consider 2 outcome observables. So these are operators with only 1 and -1 as eigenvalues. So it's just some projector minus another projector, where these projectors sum to the identity. And then the probability of measuring a 0 is like the size of the overlap of whatever state you're measuring with pi 0. And the probability of measuring 1 is just the size of the overlap with pi 1. So for example, the identity is a trivial observable. So the only eigenvalue of the identity is 1, meaning that if you measure the identity on any input, you will always just get a 0. So that's trivial. On the other hand, the standard Z matrix, it's basically just a computational basis measurement. So if you measure a state ket 0, you'll get 0, and if you measure a state ket 1, you'll get 1. Whereas X is just a measurement in the plus-minus basis. And then Z tensor Z, which has this form, it's still a single-bit outcome, but you're actually measuring the parity in the computational basis. Because you'll get 0 if you have 0, 0, or 1, 1, and you'll get 1 if you have 0, 1, or 1, 0. So it's a measurement of a single bit that is just the parity in the computational basis. Okay, so if you have 2 commuting observables, that means they're compatible, and you can measure them both without, in any order. So if they don't commute, then, in some sense, measuring one of them will damage the state so that the second one doesn't get the same outcome. But if we have commuting observables, they're compatible, and we can just measure all of them. And in particular, we have that all of the observables in any column or all of the observables in any row commute, which is why in our strategy it's fine for the provers to measure all of the observables in a column or a row. So for example, the second prover, if he gets 1 as input, he'll look at the first column, and he'll be able to do all of these measurements because they commute. These observables commute. And what are these measurements actually? I mean, so each prover has a 2-qubit system, which is half an EPR pair. And so the first I tensor Z is just measuring the second qubit in the standard basis, and so that will just output some bit. The second measurement is Z tensor I, that's measuring the first qubit in the standard basis, so that's going to measure a bit. And once both of those measurements have been made, we know that the state is necessarily, whatever it was before, is now collapsed to B2, B1. And then the final measurement in this column, Z tensor Z, is going to measure the parity of these 2 bits. So it will always get B1 plus B2. And these always sum to 0. And that's because that's true because the product of these 3 observables is the identity. And so whenever we do the 3 measurements in a column, the results always sum to 0. So this constraint is satisfied. And similarly, whenever the first prover measures all 3 observables in a row, well, here the product in the rows is minus the identity, and for similar reasons, that means that we'll always satisfy the condition that these will sum to 1. And then finally, they always use the same measurement for the place where their inputs overlap. So when you measure EPR pair halves with the same measurement, you always get the same outcome, and so they'll always satisfy this consistency constraint as well. So this is a winning strategy for the magic square game. It always wins. And we know that's not possible classically, and so this gives a way for 2 provers to prove that they're at least somewhat quantum. But we can actually say something even stronger, which is that this strategy is a unique strategy that wins with probability 1 in some sense. So if the provers win with probability 1, it must be that they're employing this particular strategy in a sense that I'll describe shortly. But that's actually very powerful because it means that we can actually use this game not only to test that anything quantum is happening at all, but to test these particular measurements. So we can actually test that these observables have been measured, which gives us a way to test measurement devices. Now, one sort of issue in actually implementing such a test is that you can never know that 2 provers are winning with probability 1. And so we need a slightly stronger statement, which says that if the provers win with probability close to 1, then it must be the case that their strategy is close to this sort of unique strategy. And that's also known about this game, and such a statement is called a robust rigidity theorem. This sort of means that we can actually view the game as the verifier giving instructions to the provers, telling them, please do these measurements and send me the results. And the only way for them to win the game is to actually follow her instructions. So this allows us to have some scenarios where the verifier dictates to some quantum measurement device or person with a quantum measurement device a measurement that they should do and actually have some confidence that they have done something close to those measurements. So in general, a robust rigidity theorem is a statement about a game where a game consists of a set of questions, answers, and a relation that determines whether the players have won the game. But the questions we can always view as just being sets of observables. So we can always consider that the questions are just instructions saying, please do these measurements. And a robust rigidity theorem says that if the players do the measurements they were instructed to do, then they will win with some probability C. And if they're winning with probability close to C, they must have done the measurements they were instructed, or at least close to those measurements, or it wouldn't be possible. So if we have a game and a robust rigidity theorem for that game, it gives us a way of testing the observables in that game, in the question set of that game. Okay, but so that's very powerful, but as I mentioned before, we can't actually really test an observable. So one reason is you could never test one observable. I could never say, okay, I want you to measure the Z and give me the answer. I can never know just by asking you to do that you have done Z. I mean, that would require me to have fixed a basis for you to work in, and I can never force you to work in a certain basis. I can never make you use, say, the spin degree of freedom of some kind of electron or something, rather than the path degree of freedom of a photon, or I can't enforce that you didn't encode your whole system in some kind of error-correcting code, which would of course mean you're working in a different basis. So I can never test a single observable. The only thing we can actually test are relations between observables. And so what are some examples of what I mean by that? Like one very simple example is commutation. So we could test, we have two observables A and B, and we can test if they commute. And that's very simple. The verifier will ask the first prover to just measure both of the observables and send the results. And the second prover will be asked to measure one of the two observables at random and send the results. And they'll win if, if W is A, then BA should equal BW, and if W is B, then BB should equal BW. Now this is a game that does not distinguish quantum from classical players, because classical players could also win this game, because classical players have commuting operators as well. They can just have a pair of shared random bits, and one of the observables is just going to be to look at the first bit, and the other observable is going to be to look at the second bit, and these are commuting. So this game doesn't tell us anything that they're doing as quantum, because classical players also can have this relation. But we could have this in combination with some other relations to make a sort of non-trivial set of relations. This could be a sub-protocol, like a larger game. And in fact, this is actually a sub-protocol of the magic square game in some sense. And I already mentioned that in the magic square game, we are kind of testing the commutation relation. So it must be the case that all of the columns commute and all of the rows commute. So that is something that we're testing. But we are actually testing even more than that, because if all of the entries in this matrix commute, we would have that the columns commute and that the rows commute. But we would not be able to satisfy the other constraints. So if we had X and Z commuting, so all of these entries commute, then it would be the case that if you take the product of all entries by first taking the product of the columns and then taking the product of those products, then you would get the identity. Whereas if you first take the product of each row and then take the products of those products, you get minus the identity. And that means that something doesn't commute. That means that some of these entries have to anti-commute. And in particular, it must be the case that observables not in the same row and column have to anti-commute to actually win this game. And so this game is not only testing certain commutation relations, it's also testing anti-commutation relations. And in particular, these relations that are tested here define this group, which is similar to the Pauli group, but on 2 qubits, but without the complex phase. And so this game tests all the relations that define this group. So we can test by using this game that these particular operations are being done, at least in some representation of the group. So we can't know for sure that a particular one of these measurements is being implemented in a certain way, but we can know that this is the group structure of the observables being done by the verifiers, or by the provers. And so we can extend this to a test of arbitrary Pauli groups. But if we want to test Clifford measurements, which we do, because that's what we need for modifying the other protocol, we need more relations. So if we have a Pauli group P, so some n-qubit Pauli group, the corresponding Clifford group is defined like this. And the important part is that it's defined by relations. In addition to the Pauli relations, we also need certain conjugation relations. And so we also need a way to test these kind of conjugation relations. And just to give some idea of how we do that, if we have 2 operators defined like this, then these operators commute if and only if this conjugation relation holds. And so that means that by testing the commutation of these 2 operators, and also that they have the structure that I've shown here, that's enough to test conjugation relations. And so we can build up a game that tests the Clifford group using this conjugation test, which I have not fully described. But I won't go into more detail on how we build up the game. Now let me just say what we get. So we have a new game in a robust rigidity theorem that allows us to test m-qubit Clifford observables. So the questions include all of the m-qubit Clifford observables, but this is not the first such game. Something that is special about this game is that we have a constant, our function delta is constant in m. So previous results of this form have had a delta that is polynomial in m, which is the dimension of the system, which requires that epsilon be inverse polynomial in m. And so this requires a lot of precision, which gives a polynomial overhead. But here, our function delta is constant in the dimension of the system. And so we don't have any kind of overhead except constant by playing this game. OK, so this is a way for us to test Clifford observables, which, if you remember from the end of the previous section, is going to be very useful. We can now combine this with the EPR protocol to get a two-prover protocol. So we'll start with the EPR protocol. So remember, we have a verifier with a measurement device who's going to measure EPR pair halves, and we have a quantum prover. And we're going to have our two provers simulate the verifier and the prover respectively. So one of our provers we call prover V for verifier, and this prover is just simulating the verifier from the EPR protocol. Whereas our second prover, prover P, is simulating the prover from the EPR protocol. So remember, this prover V, or this verifier from the EPR protocol, should at some point do some measurement. So for example, our verifier might now say, OK, it's that time in the protocol that you're supposed to measure observable Z on one of your EPR pairs. And if she's honest, she'll do the measurement and send it back to the verifier. And generally, that's how this protocol unfolds. So what that means is that if we have everyone honest, the prover V and the verifier are simulating the verifier from the EPR protocol, and prover P is simulating an honest prover from the EPR protocol. And so by the completeness of the EPR protocol, everyone's honest, so they'll learn the output of the computation. On the other hand, if prover V is honest, but prover P is dishonest, still prover V and the verifier are simulating the verifier from the EPR protocol. Now prover P is like a cheating prover from the EPR protocol. So by the soundness of the EPR protocol, our verifiers will reject. Now, the only remaining problem is that we cannot assume that prover V is honest. Now, in the EPR protocol, you can always assume the verifier is honest because, otherwise you can't help anyone. But here we cannot assume that prover V is honest, so we have to take care of that. That means that when it's time in the protocol, our actual verifier says to prover V, it's time for you to measure the observable W and send me the result. We actually don't know if prover V is going to do that. So the way we'll get around this is by using the robust rigidity theorem that I mentioned. So sometimes the verifier will be sending an instruction to prover V and saying, now it's time for you to measure W and send me the result, because it's part of running the actual protocol to do the computation. But sometimes it will actually be that the verifier is playing a game with the two provers. And if prover V is cheating, she'll be caught. And prover V cannot tell the difference. Prover V is just getting an instruction of a measurement to do. So she doesn't know if it's because it's a game or if it's because it's part of the protocol. Prover P can tell the difference. He knows, oh, we're being tested now. But there's nothing he can do about it, because if he doesn't return the right thing, then they will be rejected. And so even if prover V is dishonest, the protocol is still sound. OK, and using these ideas, we actually get two protocols depending on the order in which we interact with the provers. So I'll just summarize. The first is called a Verifier-on-a-Leash protocol. And it has complexity g log g. The number of rounds is proportional to the t depth. The total complexity is still g log g. It's just spread over a potentially larger number of rounds. But the t depth is certainly not more than g. So the total overhead is still g log g. And it has a nice property that's blind, meaning that neither prover can learn the input, and therefore we can also hide the computation if we want. If the provers later decide to come together, they can together learn the input, though. Okay, and then our second protocol is called the dog walker protocol because it has a kind of complicated structure of leashes. It also has complexity g log g, but it has the nice property that the number of rounds is constant. The downside is it is not blind. One of the provers just learns the input completely. And one reason that it's nice to have a constant number of rounds is, well, it would be nice to be able to enforce the non-communication between the two provers by having them be space-like separated. And we cannot do that here because, even though we actually can have as few as 2 rounds in the dog walker protocol, but 1 round has to happen first, and then we get the output from one of the provers, and then we communicate with the other prover. And so since our message to one prover depends on the other prover, they could have communicated in the time it took us to receive a message and then send another message. But by reducing the number of rounds, we get kind of closer to a protocol that we can actually enforce non-communication through space-like separation. And in fact, one of my co-authors, Alex Grillo, actually did manage to very recently give a protocol, which is the first 2-prover protocol that can enforce non-communication through space-like separation by modifying our protocol. So I'll end here. More details on our paper is the first link, and the new protocol where you can enforce the non-communication by space-like separation is the second archive number. So thank you very much.